Yes, sir. Yes.
Okay, so we'll continue from where we were. So then I'll just talk about it.
I have allowed all participants for recording.
Yeah.
Yeah.
So
Yes, sir.
Yes, sir. We have
So let
started.
me allow you also.
yes.
I'm not sure
Let
whether I have
me.
allowed you all.
Okay. We replace sinusoidal waves with localized functions, having a Fourier support that is wider at higher frequency. So essentially, you're changing the bandwidth based on the frequency, center frequency. At higher center frequency, it's proportional to center frequency. At higher center frequencies, we have higher bandwidths. That is the idea in a wavelet transform. So the idea here, you see, that is more difficult to understand. What is easier to understand is when you go to higher frequencies, you need to be more localized in time. So you try and make the functions narrower at higher frequencies. And you say essentially have one function, which you call the mother wavelet. The mother wavelet is scaled by various scaling factors, scaled on the independent variable. Please note, it's a scaling on the independent variable. So as a consequence, what happens? When you scale the independent variable, it also scales the independent frequency domain variable. And the scaling is in the opposite way. So if you stretch the function in time, it compresses the function in frequency and vice versa. So when you compress the function in time, it stretches the function in frequency, and therefore both the center and wavelets are typically bandpass functions. They are functions which are essentially localized to around a non-zero center frequency. In fact, wavelets have to be bandpass. They cannot be low-pass functions, right? Which means that they must have a zero mean as a function. So what is a wavelet transform? A wavelet transform is essentially a correlation of a function. When you say you're talking about the wavelet transform of a function x, you're correlating the function with different dilates and translates of the mother wavelet, psi. And at different dilates, the mother wavelet essentially spans different frequency bands. At different translates, the mother wavelet spans different time zones. So you're trying to move around in the time domain and the frequency domain all at once. That is the idea in a wavelet transform. So now what happens when you do this? What are you doing in the Fourier domain? The Fourier domain, you're multiplying the Fourier, when you correlate, you're multiplying the Fourier transform by an appropriate modified version of the Fourier transform of the wavelet, right? So of course, the Fourier transform is scaled, and the Fourier transform would also be multiplied by a linear phase factor depending upon the translation. So you see here, of course, now the way to understand it is that linear phase factor would come in the inverse Fourier transformation. So at a particular scale, when you take the wavelet transform, you're just multiplying the Fourier transform of the original function with the appropriately scaled version of the Fourier transform of the wavelet. And when you take its inverse wavelet transform, then you're going to multiply this by a linear phase factor and then integrate. So that automatically takes care of translation at different translation parameters. Anyway, here we are talking about what happens, the overall Fourier transform of the wavelet transform at a particular scale. That is what is being indicated here. So let the Fourier transform be centered at a certain frequency eta. Then when you scale the Fourier transform, you scale the wavelet function in the time domain by a parameter lambda. It's also scaled in the frequency domain by the inverse of that parameter, lambda inverse. And the support also has a different center now. If the original support was at eta, now the support has changed proportional to the scaling factor. That is what needs to be understood. And the bandwidth also has changed. So both the support, where the support, the center frequency has changed and the bandwidth has also changed. Of course, here I'm not going into all details of the wavelet transform. We're just trying to give you a quick recap of the wavelet transform. That's because we assume that some of you might be familiar with the wavelet transform and we have some idea. So we are trying to give you the essential features. I'm not going into all the mathematical details. So the wavelet transform at a particular scale. Now, typically wavelet transforms are calculated with what are called dyadic scales. Dyadic means in powers of 2. So a wavelet transform can be calculated at a scale 2 to the power j, which we are denoting by W subscript j. And it essentially keeps wavelets of frequencies for which small j, the parameter which you're using to change the scale is less than capital J. Now, let me try and interpret this non-mathematically, or in a simpler way. See, what we are saying is a wavelet transform captures at a particular scale, wavelet transforms capture information in a particular band, and that band expands as you go to higher frequencies. Now, very often, instead of just doing a wavelet-based capture, we also bring in what is called a scaling function. So we bring in the scaling function phi, which when appropriately, so there's a scaling function, there's a wavelet function. The scaling function captures all the frequency components up to a particular frequency. The wavelet function captures the incremental information in a particular band, right? These are again technical details, but this figure illustrates a lot of things. Let me explain this to you. Here, this brown function that you see here is the Fourier transform of the scaling function. It's essentially a low pass scaling function. A scaling function is always typically low pass. Yeah. So when you scale the scaling function, the effect is to retain the center frequency at 0, but the band expands. So it essentially captures more and more band. And the wavelet function, as you see here, psi, omega with different dilation parameters, moves along the frequency axis. So it captures the incremental information between two scales. Let me again repeat that. When you take the scaling function and you use two different dilation factors on the scaling function, it captures two different extents of band all around 0. When you use the wavelet function, it captures the incremental information at that scale, what is new to that scale. And that is captured by what you see here. So the wavelet transform at this green scale would capture the incremental information in this band. The wavelet transform at this blue scale will capture this incremental information, and so on. The pink scale, it will capture this incremental information, and so on and so forth. Now, the wavelet transform, there are issues about its translation invariance, right? So it's not very straightforward to make it translation invariant. Now let us just say a little bit about translation invariance. When you want it to be translation invariant, in fact, now I wouldn't really go into all the details here, but suffice it to say that what translation, when you talk about translation invariance, what are you really saying? If you translate the image, if you move the image, it should not significantly affect your representation. So, you are focusing on the features that are of interest to you, and the translation should not affect that. All this is captured mathematically here, right? How is all this achieved? If you want to use the wavelet transform, it is achieved by something called a scattering convolutional network. So, briefly speaking, a scattering convolutional network has a structure shown here. You're taking the original function and using multiple scales of the wavelet transform, and then garnering information from all these scales to make certain inferences on higher order features. This is a good point for me to hand over to Sagar. So I'm going to now hand over to Sagar, because he's going to now describe to you in detail the work that he has done for his dissertation. And you see, as I said, our focus was not so much to talk about the details of wavelets here, but just to give a quick recap on wavelets so that you could be prepared for understanding what work Sagar did for his dissertation, and maybe also to some extent go through the demonstration on your own that he's going to show you. So now I'm going to hand over to Sagar. I'll stop sharing myself and I'll request Sagar to share from the point at which I have handed over to him. So Sagar, over to you.
Yeah, sure. Yeah, am I audible?
Yes, you are.
Okay, yeah. Yeah, thank you, Professor Gadre. I'll start my screen sharing. Is it visible?
Yes, it is.
Yes.
Okay.
Yes.
Yeah. Okay. Yeah. Hi everyone. I am Sagar. I'll continue from this slide 21. So before I continue, I would like to say that Professor Gadre indeed give a very nice explanation of this concept of scattering wavelet network. And so I would like to say that some of you who are not who are newly getting exposed to wavelet might find it a little bit difficult to understand these mathematical equations, but it's okay. So those who have gone through wavelets will try to understand it better. And yeah, so I'll start from here. And before that, I would like to add one more thing, that the techniques which we are going to discuss, one which is multi-resolution and the another which is based on deep learning, are applicable to other biometrics as well. But for this seminar, we are considering the ear biometric. Okay, so with that I begin. So Professor Gadre has mentioned that this wavelet transform is a bandpass filter. So we can see from equation 9 that when we integrate x convolved with phi lambda, we get a 0. So this is trivially invariant. So we want to avoid this. Why this is 0? Because there is no DC component in this expression, since wavelet extracts a particular band in frequency. So there is no DC component. So to get an invariant, which is not trivial, what we do is apply a modulus operator, which is a non-linear operator. And once we do that, and then if we integrate, we get a non-zero value. So why this happens? The proof has been given by the authors in their paper. You can see in the references. So I won't go into that right now because it may not be that important for in the current context. So I'll proceed from there. So the thing to note is we get a non-zero invariance. So we can see from equation 10. Now x convolved with phi lambda extracts a particular band in frequency, and if we take modulus and we integrate, we get a non-zero value. So basically we are taking the DC value of this expression, which I have highlighted here. So now what about the other frequencies? The higher frequency information is lost. So to recover that, we again convolve with another wavelet of phi lambda 2 of different scale, and then we keep on repeating this to get higher order information, which we remove by taking this integral, modulus and integral. So we keep repeating this process, and we get what we call a scattering convolution network. Okay, yeah. So we can see that the figure shows a two-layer network. So at layer 1, what we have is we have the image f of x comma y. F of x comma y is the image which x and y are the x and y coordinates. So it is a two-dimensional signal, and we convolve it with different scales, wavelets of different scales and orientations. So we get a layer 1 representations. So if we again convolve this second time, as we can see here, we get second layer information. So this is how scattering wavelet network is constructed, and we use it to extract features of ear images. So as I mentioned earlier, this can be even used for other biometrics as well, but we will use it for ear in this context. So yeah. So one thing to note is this has a similar structure as compared to convolution neural networks, but the difference is here the filters are wavelet filters, and they are handcrafted, and they are not learned from the data, and they are handcrafted. So we use it for extracting features. So it possesses different various important properties. The one being the translation invariance, local translation invariance. It also has a small deformation invariance property, it is invariant to small deformation, and it preserves signal energy because we are not losing any information as we are extracting it using wavelets of which are bandpass filters. So we remove the possibility of losing any frequencies. So we preserve the signal energy, and in doing that we retain the higher order information. So these are the important properties which we have while using scattering network. Okay. Okay. So moving forward, we use this network for ear recognition. So for this, we use a Mollet wavelet, which is a Gaussian wavelet multiplied with complex exponential. So it is a complex wavelet. So this is the uh, exponential term, and this is the Gaussian part. And we construct multi-scale wavelets having different orientation to capture the orientation information in ear images. And the averaging filter is chosen to be Gaussian. So the way we will proceed is after I explain this slide, we'll move to a demo which will use a library to extract scattering features, and I'll show you how to do the evaluation. So yeah, so the steps for feature extraction is as follows. First, we convert the image to grayscale, and we normalize any pose variations, such as if the ear is tilted or oriented in different direction, we bring it to a standard configuration, which is vertical, and then we resize it to 100 cross 100 with bilinear interpolation and do some enhancement techniques. Then we use this pre-processed image to we give this pre-processed image to SCATNet, and we get our features. So from this point, I'll move to the demo session of this technique, and after that, we will look into a deep learning based technique for feature extraction. I'll explain a theory in very brief, and then we'll also have another demo of deep learning based technique. So yeah. So for this, I have made the workshop content folder, so which will be shared with you. I request organizers to share with this content with participants. I'll share the folder with you. So it contains the data set, year data set. Specifically, we'll be using IIT Bombay data set, which we have created, and uh, we will use these files for both the experiments, scattering network and deep learning. So I'll explain you how to do that. So let's start. The first thing which you'll have to do is you have to go to collab.research.google.com, and you will have to sign in if you're not done. So after sign in, you will have you can pick up the files. So yeah, before that, you will have to upload the content which I'll be sharing on your Google Drive, and from there you can access the IP YNB files. So there are two files which we'll be using for this session: the SCATNet ear IP YNB, which will be used for a scattering experiment, and the CNN_collab for the CNN experiment, which will be explained very shortly. So I open this. So what is Google Collab is it's a platform provided by Google to have to run your experiments, Python experiments mainly, and it allows you to have a GPU. It allows you to use GPU, which is a graphical processing unit, which
Sagar, are you sharing your demo screen, or you're not sharing
okay,
it
okay.
right now?
I'm
Yeah.
not. Oh, sorry.
Yeah, you'll have to share your demo screen.
Yeah. I missed that. So thanks for reminding.
I was thinking of, I mean,
Yeah,
is
no, it's okay. Let's see, you can
yeah.
share the demo screen.
Okay. So, mm,
You can close this and share the
okay.
demo screen.
Yeah.
Yeah, that's
Is it
better.
visible?
Now it's
Okay.
visible. Yeah, you can go on from
Okay.
here. No problem.
Okay. Yeah. So quickly repeating the last few lines. So what we have to do is you have to go to collab.research.google.com, which I have just gone here, and uh, so let me repeat that again. Is the sound volume is good?
Yes, it is. It is.
Okay.
Yes.
Okay. So the first thing is you have to go to this URL and you have to sign in if you are not already done. And the content which I'll be providing, the workshop underscore content folder as shown here, you'll have to upload it on your Google Drive, and with the same Gmail ID you have to sign in to Google Collab, and then you will get this screen. If you have not got this screen, you can go to file, open notebook. So you arrive here and then go to Google Drive and click the file getnet year underscore IPYNB. So it opens here. So Google Colab allows you to use GPU, which helps in parallel processing and faster execution of codes. So, so the platform is like this. So each cell is a code section which you can run by highlighting it and then pressing Shift Enter or Control Enter. And you have to do a few settings if for the first time. So you have to go to runtime type and select GPU. I have already done that. So if this option is not there, you have to select GPU here. By default, it will be none. You have to select GPU, then save, and then highlight this, select this cell, and press Shift Enter. So it is running. You can see that it is getting connecting to the GPU server, and once it allots, it will show, it will initialize and show the show this. So you can see that we have been allotted a GPU memory. So around this much GPU has been allotted to us. Sorry, this is a RAM. The GPU is 16 GB of GPU has been allocated to us. Okay, so now this is the important part which needs to be done. So we need to access the data set for this experiment. So how we do it is we link this file, this Google Colab, to our Google Drive. So you have to just do Shift Enter, and you have to click this URL and sign in with the Gmail ID on which we have uploaded the workshop underscore content folder. So all these email IDs should be same. You have to use the same email ID, and you have to copy this code and paste it here. So with this, we have linked our this current session of Google Colab to the Google Drive. And for the first time, you will have to install this KYMATIO library. So this is the scattering wavelet network library, which is prepared by the authors of ScatNet, and you have to install that first. I have already installed, so I'm not running it. So it will take 1 or 2 minutes. Then these are the few imports which we need to do. Okay, I think I have to install it again. Okay, so once that is done, so if you do not run this, it will show this error that this library is not installed. So you have to do that. So this is done. Then, so what we'll do is, so this library KYMATIO provides this class scattering 2D, which we initialize this way, and J is the number of scales, and the shape is the image size, which is 100 cross 100, and L is the number of orientations of Mollet wavelet, and J is the number of scales. So with this we initialize the scattering of this function, and we move it to CUDA. So what it does is we now if we do this, it will do the operation on the GPU. So this is one important step. So if we just do list, so workshop content is the folder. If you just list, you will get these files. So if the linking has been properly done, you will be able to see the dataset folder. Then we define this train directory and test directory. So what this is this data set is divided into train and test, and each so there are a total of 100 classes. There are a total of 100 classes, each containing left and right ears. So in this case, we have done the pre-processing, that we have aligned it to common configuration, and we have put it in a standard orientation. So all these are oriented properly in a vertical direction, and they are the left ears are flipped, meaning they are in a fixed orientation. So I have provided you the pre-processed images to simplify. And then yeah, so this is it. So this is a sample experiment. So I am opening one image of the first image, and trying to pass this image to the scattering object instance, and I'm printing the feature size. So I got these features. So there are 81 feature maps, each of size 25 cross 25. So the 81 filters have been used in total here. So how this why this 81 is so you have total of 2 scales and 8 orientations, and so this number, so it's like if I go into this, so you can check this out in the paper. So we have we got 1 scales, and we repeat it again. So this is a permutation problem. So if you just do it manually, we'll be able to get this number. So if we change the number of scales and number of orientations, this 81 number will change accordingly. Then these are the functions. For more details, you can check the documentation of this KYMATIO library. So this I'll just proceed quickly just to give the glance of it. So this cell, I'm plotting the filters before doing the feature extraction. I'm plotting these filters. So we have 8 orientations and 2 scales. So these are Mollet wavelets, which is Gaussian modulated by exponentials. Then this is the low pass filter. Okay, so and extract the features, and then keep on appending it to this variable. So at the end of this loop, we get the features for all the images. So there are a total of 400 images, and we get the features. So this number represents all the coefficients. So it is, so once we get these features, we flatten it out in one array. So 81 into 25 into 25, we get this number. So this is the length of our feature vector for each image. So yeah, you have to run this. So I'm not running it for now. It will take some 1 or 2 minutes. So once we, I think I'll have to run it because, yeah. So once we do that, then we use when we do the so there is one more step. We do the log transformation, because so the range of this feature coefficients is very high. So to bring it to a shorter range, we do a log transformation that increases the accuracy by 2 to 3%, and we do the matching, and we get the accuracy as 92.5. So the purpose of this demo is to be aware about this library and how to use it. The more details you can have a look at this, you can play with all the functions. There are today examples. So you can do with, you can try other data sets as well, and all the things. And you can even see a plot and see the features, the 81 features which we have. You can even plot and see. So yeah, so this was the scattering wavelet part. So I'm sure you can do this. So I'll move to the deep learning part. Okay. So now moving to deep learning part. So this technique, the next technique is the deep learning based technique for feature extraction. So I'll, in 1 or 2-3 slides, I'll cover a bit of theory. If someone is new to that, it will be good to go through. And if someone is already aware, please have patience for a few minutes. So this is a CNN network. So what we have is, we have the image, and we define filters, which we call convolution filters. And we have different layers of convolution filters. So, and these are trainable. So we train these weights of the filter using the training data set, and then we get when we are satisfied with the accuracy of the train set, we evaluate it on the test set. So these are the convolution filters, and at the end, this is a fully connected classifier which will classify the image, the input image, into one of the classes. In this case, it is car, truck, van. In our case, it will be the image of person 1, person 2, person 3, and so on. You can go through this link, and they have provided very nice insights of CNN. Okay, so these are the convolution neural networks.
So Sagar, what we'll do is we'll give them 1 or 2 minutes now, so that they can go over the link. Yeah, okay. And then we'll commence our session again. Yeah, we can just give them a couple of minutes to go through.
Okay, so shall I open it here from my end?
Yeah, you can open it from that, and just open it from the end and give them a couple of minutes to go through. Yeah.
Okay. Okay. So someone is already aware of this, so it will be a repetition. So I directly prefer to have the link here so that they can.
Yeah, no problem. But I think let them, you can just run through it and give them a couple of minutes.
Okay. Okay. Yeah. So we have the input image, and we define a kernel, which is so this is a simplified version.
Yeah. So we'll just we'll give them a couple of minutes, and we'll. Yeah.
Okay.
So we'll wait here for a couple of minutes, huh? So we'll.
Sir, session is ending now. It will take few minutes to prepare the file.
Yeah.
And then
so
probably
you have stopped recording. I hope you have stopped recording.
last 15-20 minutes are left out. Then again we will join for final recording, final
That's
section.
right. That's right. Right. Okay. So now I hope you have stopped recording.
So shall I